Okay, today we're going to look at the mass of light, trying to get the mass of light from the relativistic mass equation. Here's our relativistic Einstein mass dilation formula. M equals m0 divided by the square root of 1 minus v squared over c squared. If we let v equal c in here, of course, we'll get c squared over c squared. 1 minus 1 is 0. And some constant over 0, of course, is infinity. So our mass here can equal, if m0 is some constant greater than 0, it can equal infinity. Or if m0 here is equal to 0, we have something called an indeterminate form, which in calculus we call. So we use L'Hopital's rule, knowing the functions that these are. But just to list the three solutions that can come out, one is that if this mass is equal to 0, then this mass will come out to be equal to 0. If m sub 0 is equal to 0, this mass could come out to be infinity, which is kind of what happens over here also. And if m sub 0 is equal to 0, this could actually come out to be some constant. Okay? Now, if we resolve this equation in this manner for m sub 0 and write it like this, then we'll stick c into here. Of course, we'll get 1 minus c squared over c squared, 1. 1 minus 1 is 0. 0 times m should equal 0. If m is equal to, if the relativistic mass, this is the rest mass, this is the relativistic mass, if the relativistic mass is equal to 0, of course, this would come out to be, the rest mass would be 0. If it was like some constant, then at a velocity equal to c, you would get the rest mass equal to 0, which no matter what m was, as long as it's not infinity, because if it's infinity, then we get infinity times 0, which again is what's called an indeterminate form, infinity times 0. And so if the mass is infinite, then there are three possibilities for solutions for the rest mass, and that is it's either equal to 0, which is this solution over here, it's equal to infinity, or it's equal to some constant. Okay? So we see that here both solutions will come out to be 0 here. As opposed to here, we only have one solution that comes out to be 0. So it's a lot easier to see that the mass of light is equal, the rest mass of light is equal to 0 in this solution here than any others. If we graph this mass, relativistic mass, as a function of velocity, so relativistic mass on this axis and velocity on this axis, notice that if you stick in 0 in here, you'll get just 1 minus 0, so m0. So at velocity equal to 0, right here, you'll get the relativistic mass is equal to m sub 0. Okay. Of course, as the mass as the velocity increases, the mass also increases. The relativistic mass increases in this equation to infinity. But however, we know that when the velocity of the particle actually hits the speed of light, it actually has to become light, and therefore the mass has to be, the relativistic mass has to equal 0 right here. So we have something called a jump discontinuity, where the function is going up to infinity. The relativistic mass is going to infinity as the velocity of the particle goes to c, but then at actual c, we have to have the relativistic mass and the rest mass equal to 0 right there. Okay? All right, well, thank you for watching this video, and I look forward to any comments at the bottom.